Hello, welcome to this lecture again. So in today's lecture, we'll be defining the numerical technique that can be used to solve for the weights of a risk parity portfolio, right? And after that, we will try to see the algorithm that is used to solve that numerical optimization problem. Okay. So before starting, let us just redefine the marginal risk contribution. Okay. So marginal risk contribution of any asset I that we saw is basically weight of asset I into its variance square, and then summation for all j which is not equal to I omega j, and then covariance of I with j divided by. Okay, this marginal risk contribution can be also written in terms of the matrices. So basically this is defined as this concept. Okay, so basically what I'm trying to say is the upper numerator is the denominator is very clear, right? We have seen this notation. The numerator can be written in this way, basically, where this means the ith row of this matrix, ith row of the multiplication of variance covariance matrix and the weight matrix. Okay, so we have defined in this way because it will be easier for us to write in Python. Okay, and you can indeed try to see multiply these two matrices and try to see that ith row of this matrix will indeed be the numerator of MRC. Okay, so both the notation are interchangeably used in basically to define marginal risk contribution. Okay, now let us go back to what we have to see. So basically today we have to discuss numerical optimization problem, right? So let us define the first technique that is used to solve for the weight W. Okay, so the first technique is, let us define the first problem. So the first numerical optimization problem is weight matrix W will be minimum, will be that W weight matrix W which gives you the minimum value for the function f. Okay, so this is our objective function under the constraint. So basically what are the constraint? The first constraint is that weight of all the matrices, weight of all assets should be 1, sum up to 1. So basically this is the condition, that weight of all assets should sum up to 1. And then the second condition is that weight I should be greater than 0 but lesser than equal to 1. So this is the second condition. What is FW? So FW is for us is basically summation for all j, summation for all I from 1 to n. Okay, and then risk contribution of asset I minus risk contribution of asset j. So basically omega I into MRC of so basically MRC of I minus omega j into MRC of j. Okay, square. So basically FW is nothing but summation of a squared differences of all possible combination. Okay, so basically you are subtracting the risk contribution of all possible combination, basically RC1 minus RC2, RC1 minus RC3, RC1 minus RC4, RC1 up to RC1 minus RCn. Similarly then you go for RC2 minus RC1, RC2 minus RC2, RC2 minus RC3 up to RC2 minus RCn, and then you square all the differences and then sum them. Okay, so basically you get a term which is the objective function. Now this objective function will be 0 when all the risk contributions are equal, right? But this is not the case that you will find in the real world. This risk contribution cannot be exactly equal, and that is when you have to solve for the you have to settle for a value, a very lesser value of FW. So basically you have to settle for a tolerance limit. So basically you will put a convergence criteria. So so up to that limit, so you want to minimize FW. So basically you want to keep FW as low as possible. So that W will be the answer which gives you the lowest FW given the constraints are satisfied. Okay, so basically that is our risk parity portfolio, right? And we'll be defining our second so this is one of the problems. So you can try to solve this numerical optimization problem, and then the weight that you get will be the weight of a risk parity portfolio. There is one another alternative to this problem, wherein what you can do, you can define the problem as something like the weight. So first you will try to get y will be something like minimum of this under the constraint that summation for all ln y I from 1 to n is greater than equal to c. Okay, so and then the second constraint is basically weight I should be greater than equal to 0, and c here is an arbitrary constant. Okay, so you can try to solve for this problem as well. This and after you get for y, you basically you can normalize y. Okay, so how can you normalize y? So basically from y you can get the weight w. How? So basically this will correspond to weight I divided by summation for all I y I star. Okay, so this is how you normalize y. So basically the y matrix that you will be getting from here won't be normalized. Okay, so you can normalize it using this technique, right? So this will be the weight w. Now you may ask, how can I? So now you may ask that you are satisfied that this weight is indeed the risk parity portfolio weight, but how does this weight correspond to the risk parity weight? Okay, so let us try to see it. Okay, so and then you will get it basically. So let us try to form the Lagrangian of this object. This is the objective function, right? And these are the constraint. So let us form the objective function. So if you form the let us form the Lagrangian basically. So if you form the Lagrangian, this will be lambda c. So these are the Lagrangian parameters, and then this would be, first we have to write the objective function. Okay, and then the first parameter and the first constraint, and then the second parameter, and then the second constraint, right? Now if you differentiate the Lagrangian with respect to any weight yi, it would be nothing but, so this is the variance of the portfolio, and when you try to differentiate it with any asset I, you can remember that this is nothing but MRC of any asset I, right? Minus if so y is weight matrix, so y is basically y1, y2, y3, y4. So basically if you differentiate this with respect to y4, all other terms would remain 0, right? So only one terms would be so y4, when you differentiate y4 with respect to y4, that term would correspond to this term, and all other term would be 0. Similarly here you would be getting lambda c yi to the power minus 1, right? And let us equate it with respect to 0. Got it? So basically y is nothing but a weight matrix, right? y1, y2 to yn. You are differentiating this with respect to 1 yi, so all other terms would be 0. Okay, got it? From here we will be using KKT condition. KKT condition is nothing but Kern-Tucker condition, so that we will be discussing in detail when we discuss the SQP algorithm. But here let us just try to see the crux. The crux is that the minimum of the Lagrangian parameter, that is y, basically lambda I, and then yi should be 0, and the other condition is minimum of the second Lagrangian parameter, that is lambda ci. So basically lambda c, and basically the second constraint would be 0. Okay, now if you try to see it, so basically yi cannot be 0. Why? Because ln yi is not defined for yi equal to 0. That is why from here yi cannot be 0, then lambda I should be 0. So from here lambda I is 0, right? So let us try to put lambda I as 0 in this condition. Okay, so if you put lambda I as 0, then what you get? So here I have just made a mistake, so it would be lambda I. Okay, so if I put lambda I as 0, then you get this term, right? Now if lambda c also becomes 0, then for all possible values, for all values of basically asset, for all values of lambda I and lambda c, because lambda I is also 0 and lambda c is also 0, then you get the only possible solution that you get is basically when all the y are 0. So this is not a possible case, right? So that is why lambda c cannot be 0, this term would be 0. Okay, so from here lambda c cannot be 0, right? So lambda c is not 0. So if you solve this equation, this is nothing but MRC, right? So MRC minus lambda c yi minus equal to 0, and then what you get? Yi into MRC is equal to yc, right? sorry, yi into mrc. So for any value of yi, so basically for all asset I, basically you are getting a constant value. So this is the risk contribution, right? Yi into mrc is nothing but risk contribution, right? So basically this is a constant. You have proved that it is a constant equal to lambda c. So for all value of I, you are basically getting a constant risk contribution. So that is why this is also a risk parity portfolio. So either you try to solve this problem or this problem, you would be getting a weight corresponding to the risk parity portfolio. Okay. So how to solve this problem? So to solve this problem, we have to go for Lagrangian optimization technique, right? Got it? And what is Lagrangian optimization technique? Let us discuss it in very brief, because we will anyway be using the Python code to solve for the weights of yi, right? So let us just start. So basically SQP algorithm is used to solve the following kind of optimization problem. So basically you want to minimize a function for x, any value of x, okay, subject to the condition. So under the condition that there is an inequality constant hx greater than equal to 0 and there is an equality constant gx is equal to 0, okay. So basically what is the traditional method? The traditional method is that you start with forming the Lagrangian, right? So basically lambda and sigma are the parameter, okay. So if you try to solve this, this is the Lagrangian, right? So this is the Lagrangian, and then what you do, basically the standard technique is that you try to take its gradient. So basically this is nothing but lambda l. So you try to take its gradient and try to equate with 0, right? So this is the solution. So what is the Lagrangian? So if you don't know, so this Lagrangian is defined as, so basically this is the Lagrangian function. So this gradient is defined as Lx. So differentiation of L with respect to x, differentiation of L with respect to lambda, and differentiation of L with respect to sigma. So you want it to be as close to 0 matrix as possible, okay. Got it? Now so this is the convergence criteria. So you want this matrix to remain as close to this 0 matrix as possible. Now one of the traditional technique is the Newton's method, okay. So in Newton methods, what you do, okay, in Newton's method you basically have some initial guess for x, lambda and sigma, okay. So you basically make some initial guess, and then how you iterate? Basically you iterate like this: x k plus 1, x so basically then you would have lambda, so k plus 1, and then sigma k plus 1, okay. So let me write it for you, and then this is the Hessian matrix, okay. I will tell you what is Hessian matrix. This is nothing but delta square L gradient, and then we have basically, just a minute. So this is, so you have to solve for these many things. So basically this is the Hessian matrix. So this is one of the most difficult part that you might take to understand. So basically this is nothing but, so if you have only one variable, so let us so if you have only one variable, this Hessian matrix will be d2l divided by dx square. But if you have multiple variables, so for example if you have multiple constants, so for example in our case we have for example let us say we have two asset case, so w1 and w2 would be our problem to find out. Then in that case basically this Hessian matrix would be dl by d 1 d2 square w1, and then here would be dwl by d2 w2, so w2 w1, and then here it would be d2l by again d1 dw2, and then here it would be the differentiation of L with respect to double differentiation with respect to weight w2. So this is our Hessian matrix, okay. This is the gradient of h. H is our the equality constant. How do we find the gradient of h? Gradient of h would be nothing but, so for example if you say, let us say h is the basically inequality constant, right? So for example, let us say you are again discussing the two weight case. uh, Sorry, I fumbled. So it is basically two asset case. So in case of two asset case, this gradient will be dh by dw1 and dh by dw2. Okay, right? Similarly you can find this one. But in general, so in the Newton's method, this matrix is a invert. So here the inverse is there, right? So in general this matrix is not inversible. Okay, so since its matrix is not inversible, basically invertible, you cannot find out basically what is the updated. So basically you make some initial guess, right? But then you won't be able to update your initial guess with the iteration method, Newton's method. That is why there is another technique, SQP, that basically helps you find out the basically that helps you update x k plus 1, lambda k plus 1 and sigma k plus 1. So let us see how SQP does it. Okay, so basically so SQP defines a new problem. Okay, so basically you make some initial guess of xk, lambda k and sigma k. So basically you make some initial guess. Okay, and now this will be treated, all these three things will be treated as constant. Okay, now you will be solving another problem. Okay, fxk plus, let me write it for you. Okay, so basically this is the new problem. So what you do, so basically you make some initial guess for x, lambda and sigma. In our case where you have n asset case, so basically you would be having w1 to w1 w2 w3 and to wn, and then you would be having lambda and sigma k. Okay, so then you would be making the initial guess for the weight matrix w and then lambda and sigma. After you make the initial guess, you will try to find out the weight d such that the following condition are satisfied. Okay, so what is xk? So in our case xk will be nothing but our weight matrix w, right, which we already have guessed out. So that is why x, lambda k and sigma k is our kind of constant over here. The only variable in this case is d. So you try to find out, you try to solve this numerical optimization problem and try to find out that value of d which basically minimizes our objective function. We have defined a new objective function and this is our new objective function given this constraint. Okay, so you try to find out the weight d, right? Sorry, you try to find out the variable d, and once you find out the variable d, you update your initial guess. Okay, so basically your initial guess is something. So how do you update? So basically this updation is like this: xk plus 1, lambda k plus 1 and then sigma k plus 1 will be equal to xk, lambda k, sigma k plus dk. Okay, so this is how you update your x, lambda and sigma. You cannot update with the traditional method because you see that matrix was invertible, right? So that matrix was not invertible, and that is why you defined a new sub problem. Okay, so what you do? So now since for example you guessed something. Okay, so after you guessed something, you find out the value of d using this numerical optimization problem. After you find out the value of d, you update your initial guesses. So now x, lambda and sigma will be different. Now you again put this value x, lambda and k into this numerical sub problem. After you put it here, you again find out the value of d. After you find out the value of d, you will again updating your initial you will again be updating x, lambda and sigma. You will be updating x, lambda and sigma continuously until the basically your gradient of the Lagrangian becomes 0 0. So basically it becomes as close to 0 as possible. Basically, so what is this Lagrangian? This is nothing but dl with respect to dx, dl with respect to d lambda and dl with respect to d sigma, right? So this is our SQP. Okay, In our case, in case of a weight matrix, you won't only have dl by dx, but still you will be having dl by dw1, dl by dw2, right? And then these two basically differentiation of L with respect to these two parameters as well. So this is our standard SQP algorithm. Got it? So this is our SQP algorithm. If you try to see an example of SQP algorithm, this would be better, because you will be able to understand how you solve SQP algorithm. So let us try to use an example of how do we use SQP algorithm. So let us try to minimize our objective function fx equal to x minus 2 square, subject to the condition that hx is equal to x minus 1 greater than 0, and the second condition is gx is equal to x minus 0.5 equal to 0. So we want to find out our x such that our objective function is minimized under some given condition. So we will be using SQP algorithm. So first of all, what is our objective function? This is our objective function, this is the inequality constant, and this is the equality constant. Okay, so let us try to find out some value which will be helpful for us to form the sub problem. Okay, so first of all, what is the gradient of the objective function? The gradient of objective function is basically df by dx, right? So it would be 2 into x minus 2, right? Gradient of inequality constant would be 1, because differentiation of h with respect to x is 1, and then again differentiation of so gradient of the gradient of equality constant will also be 1, right? And then we have to find the Hessian as well, Hessian of Lagrangian, right? So let us write out the Lagrangian first. So basically, see, if you try to see it in SQP algorithm, you have the this is the Hessian. Okay, so in SQP algorithm you have the Hessian as well, right? So we have to find what is the Hessian of the Lagrangian. Let us see it. What would be the Hessian of Lagrangian? So first of all, what is the Lagrangian? Lagrangian in our case, first of all, let us write the Lagrangian. Lagrangian in our case will be fx is, so basically fx plus lambda hx plus lambda sigma gx, right? And what is the Lagrangian? So basically, if you try to find out the Hessian of the Lagrangian, it is nothing but d2l by dx square, right? And if you try to differentiate the Lagrangian with respect to x, you would be getting nothing but 2. Okay, got it? Now we have evaluated everything that is required to solve the numerical optimization subproblem. So if you try to see it, this is the numerical optimization subproblem, right? So we'll be seeing it in detail, so don't worry about it. So first of all, let us make some initial guess for x, lambda and sigma. Let it be 0, 0 and 0. Okay, so first of all, we have to find the value of the, so let us write the SQP subproblem. What was the subproblem? We have to minimize delta, so basically gradient of fxk, right? And then half d transpose L d, subject to the condition that hxk plus lambda hxk transpose, just a minute, greater than 0, and the second is gxk plus gradient of gxk transpose d equal to 0, right? So this is our numerical optimization subproblem. Now what is our initial guess? Our initial guess is that x is equal to 0. So if you, for the initial case, so this is our so this is right. So for the initial guess, what would be this function? This, for our initial guess, it would be minus 4, it would be 1 and it would be 1, right? So Let's just try to write it. So basically we have to minimize. For our initial case, this gradient of f would be minus 4, right? So it would be minimized minus 4d plus 1 by 2 into d. What is the this is the Hessian of Lagrangian, right? The Hessian of Lagrangian is 2, so it would be 2 and then it is d, right? Subject to the condition. Now what is h at our x? So xk is basically 0. So what is h0? So basically h0 is nothing but 1, right? So 1 plus, what is the gradient of h? Gradient of h is 1, so it's basically 1 plus 1d equal to 0, right? And then the second is that g of xk. So basically the second condition is that g of xk is 0. So what is g of xk? G is nothing but x minus 0.5 equal to 0. So it would be just a minute, it would be minus 1, okay? And g of xk would be minus 0.5, right? Minus 0.5 plus, this is 1, right? So 1d equal to 0. So now from here you get the value of d. After you get the value of d, you can update your initial guess. So from here you can see that if you solve for d, you will be getting d equal to 0.5. d will be getting 0.5. After you get d, you can update your initial x. Your x will be x initial plus 0.5. It would be 0 plus 0.5. It is 0.5. Now you have got the new value of x. Similarly you can update lambda and sigma. Lambda and sigma are updated according to the KKT condition, okay? So let us not get into that much detail, because anyway we will be solving the problem using Python code, but I wanted to give you the intuition of how an SQP algorithm works, okay? So if we try to summarize the today's lecture, we started with how to write the MRC, marginal risk contribution, in the matrix form. Then we try to define two numerical optimization techniques. Both after solving for the weights according to this two numerical optimization technique, you get for the, so if you solve one or two, either one or two, you would be getting the basically risk parity portfolio only, okay? So after you solve, how do you solve this two numerical optimization problem? So basically you see that you have one objective function and two constraint. One constraint is the equality constraint and other condition is inequality constraint. So you solve this problem using SQP algorithm. How is SQP algorithm working? So in SQP algorithm you first find out the gradient of basically all the three functions. The first one is objective function, the second, the other two are constraint. Find out the gradient of all these three. How do we find the gradient? So basically gradient of any function f is nothing but, for example, if the function f is a variable of x1 up to xn, then its gradient will be df by dx1, df by dx2 up to df by dxn. So this is your gradient, okay? Got it? Now first of all find out all the gradient, find out the Hessian of the Lagrangian. After you find out these things, make an initial guess for your weight matrix and then lambda and sigma, which are the Lagrangian parameter. After you make an initial guess, formulate the Lagrangian subproblem. What is the Lagrangian subproblem? This is the SQP subproblem or the Lagrangian subproblem that we say. So after you solve for this subproblem, you get the value of d. After you get the value of d, you update your initial guess. So basically you update the x matrix, so basically weight matrix with the d values, and then you update the condition. So basically you update the Lagrangian parameters with respect to the KKT condition that we haven't seen in detail, but that is how the SQP algorithm works, okay? So now in the next lecture we'll be seeing the Python code. If you have any doubt, let me know, okay?